Okay, so to finish out our lesson on implicit differentiation, let's return to the equation that we saw at the end of my first video, our introduction to implicit functions. We saw that this equation x cubed plus y cubed equals 6xy could be graphed, and it gives us this loop graph that we see in blue. We talked about how the point 3, 3 was a point on that graph. And we talked about how if we wanted to draw the tangent line at that point, we basically have everything we need for the equation of that tangent line, other than the slope. Okay, so now that we've learned how to do implicit differentiation, let's see how we can use that to find the slope of this tangent line. So coming back to the equation, if I take the derivative of both sides with respect to x, then on the left-hand side, the derivative of x cubed plus y cubed with respect to x is pretty straightforward. The derivative of x cubed is 3x squared. For the derivative of y cubed, remember in this case we're thinking of y as being some function of x. So we have to do the chain rule. It's going to be 3 times the inside function squared. But then to finish the chain rule, we multiply by the derivative of whatever that inside function is, dy dx. On the right-hand side, we need to be careful here because this is a product. We have 6x times y. So to do the derivative properly, we need to make sure we apply the product rule. According to the product rule, we need to start by doing the derivative of 6x. The derivative of 6x is 6, and we leave the second function alone. Then we add to that 6x, leaving that piece alone, and now take the derivative of the second one. The derivative of y is just dy dx. Now that we've taken the derivative of both sides, in the previous video that you watched with examples of implicit differentiation, what you would do next is solve this equation for dy dx. I'll mention here that we could technically stop at this point and figure out what our slope of the tangent line is by just taking our x and y value and plugging them in anywhere we see an x or a y. That would give us a whole bunch of numbers along with these dy dx's, and then we can fairly easily solve for dy dx. If you want to try that, you can try that on your own now. But what I'm going to do next is I'm going to go ahead and, just for the sake of example, go through that process again that you saw in the previous video of solving for dy dx. Either way we do it, the final answer for the slope of the line should come out to be the same thing. Alright, so solving for dy dx without plugging in the 0.33, what we would do is we want to collect all the terms that have a dy dx over on the same side. So for example, this term 6x dy dx, if I want to move it over to the left hand side to pair it up with the other term that has a dy dx in it, I can subtract this off from both sides, minus 6x dy dx. Subtracting from the left side as well. We also want to get rid of this 3x squared. This 3x squared does not have a dy dx attached to it, so we want to get rid of that. We want just terms with dy dx on the left hand side, and anything that doesn't have a dy dx over on the opposite side. Alright, so to get rid of this 3x squared, I'll subtract 3x squared from both sides. And after doing all of the subtraction, what I have is 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. Now that both terms on the left-hand side have a dy dx in them, I can factor that common piece out factoring out the dy dx, what I'm left with inside the parentheses is a 3y squared minus 6x. The right-hand side is still 6y minus 3x squared. And then finally, I have dy dx multiplied by 3y squared minus 6x. So I'll just divide that off from both sides of the equation to get dy dx all by itself. And I get dy dx equals 6y minus 3x squared divided by 3y squared minus 6x. So this expression here, 6y minus 3x squared over 3y squared minus 6x, that is the derivative of y with respect to x. In other words, that gives us the slope to the tangent line for any point x comma y that we choose. So if I wanted to know the slope of the tangent line at this point right here, whatever that point is, if I plug that into this expression that I have circled, that tells me the slope of the tangent line at that point. Now we're focusing on this point 3, 3. Let's plug that point into this expression for our derivative, and that'll tell us the slope of this tangent line that we're trying to find the equation for. A little bit of notation that I'll show you is when we're going to plug a point into one of these derivatives, dy dx, we want to take our derivative dy dx and plug in the point 3, 3. The way we say that is we draw this vertical bar next to it and write the point that we're using down at the bottom of that bar. So the way I would read this notation that I just wrote is I would say dy dx, and then that vertical bar I would say evaluated at 3, 3. So this is dy dx evaluated at the point 3, 3. To evaluate the derivative at 3, 3, again, all I'm doing is plugging 3 in for x and 3 in for y into my derivative here. So that's 6 times 3 minus 3 times 3 squared divided by 3 times 3 squared minus 6 times 3. And if we simplify, it's actually pretty easy to simplify this one because you have the exact same thing on top and bottom, just in opposite order. So this is going to simplify to -1. If you're not convinced, then you can verify that for yourself. But this -1, what it means is that's the slope of my tangent line at the point 3, 3. So what we just found is the slope of this line. The slope of this line is -1. Now that we know the slope and we know the point, we have all the pieces we need to write down the equation of this line. We already knew that we would have y minus 3 equals the slope times x minus 3, but now that we know the slope, we can fill that in and write this equation. So this equation here is the equation of that tangent line we have drawn at the point 3, 3. Now on your homework, you're probably going to want to solve for y, get y explicitly in terms of x. So you'll want to get rid of that minus 3 on the left-hand side by adding 3 to both sides. We also typically will just go ahead and distribute the slope into the parentheses just to make it look a little bit nicer. So doing that real quick, if I distribute the -1, I have -x plus 3. And then if I add 3 to both sides, I have y equals -x plus 6. So this equation right here is the equation of this tangent line that we've drawn at the point 3, 3.